So we do all of the like normal gas golfing stuff that you would probably do before launching a project on mainnet. So, minimizing state reads and writes and using the correct types if you can compress them, and doing state packing and all sort of like the stuff you would find on a Medium post. We obviously do all of that. I think where things get more interesting is trying to design your system from a cost first perspective, right? And this is something that's taken us a lot of iterations to get better at doing. And this like bundling discussion right now is something, we thought about specifically to try and not just make things like a little bit cheaper, but to actually make them like orders of magnitude cheaper, like trying to construct your design in a way where you layer savings on top of savings, and you get like this multiplicative effect rather than just like, I managed to make a for loop cheaper by using like an unsafe increment or something like that. So I think there's like different ways of viewing gas, and really like our focus where this is important, right? Which isn't always the case, but where it's important is to design first thinking about that.
Hello and welcome to episode 3 of the Devs Do Something podcast. Today's guest is Chris Maree, a senior engineer at UMA Protocol and research partner at Hack VC. Chris is a wealth of knowledge on all things smart contract development, DeFi, and cryptoeconomics. He initially got into the space as a dev, but since then ended up also pursuing a master's degree in fintech so that he had a deeper understanding of financial primitives and how the finance sector works so that he could combine it effectively with his ability to write great solidity code and smart contracts. In this episode, we go through everything from good smart contract design patterns at UMA, the UMA optimistic Oracle design, some of the low-level implementations that I thought were really cool on the Across bridge that UMA developed, and other things like some of Chris's favorite optimization patterns and his long-term vision for the space. So if you're a smart contract developer or an aspiring smart contract developer who's interested in DeFi, I think you're going to love this episode. I'd especially recommend listening to the last third as we discuss some of the things that UMA's doing under the hood with Across and how Chris specifically thinks about gas optimization and, more importantly, designing efficient smart contracts overall. I hope you enjoy. All right, so we're here with Chris. Welcome, Chris.
Hi.
Hey, so we're super glad you're here. Made the time to come talk to us today. Before we get into some of the technical things around UMA, your work, and deep dive all of that stuff, I'd love to understand just your background and how you got involved in the industry.
Sure. Yeah. So I was mining Bitcoin in like 2012 while still at high school. And my sort of Bitcoin pizza story that everyone has is I had like, I think about 150 Bitcoin back at that point. Ended up trying to sell them all for video games because there was no off-ramp in South Africa for Bitcoin. Sold them for some Steam credits and bought some games on Steam and kind of forgot about crypto until 2016, where I was doing an internship and I saw the Bitcoin price on someone's computer and like literally went to the bathroom and threw up because I couldn't believe how much money I'd like, it was a few $100 for some Steam games, and it turned into a lot more than that. And sort of fell down the Ethereum rabbit hole late 2016, early 2017, which was like perfect time to get involved in the space, obviously, with that hype cycle. Got kind of involved in a lot of like the protocol research stuff. I was very interested in like consensus mechanisms and protocol design and this kind of thing. And worked on a few startups that were in that space, some in like the edutech space and the healthcare space. And then I sort of spent some time like reflecting on like, where do I think this technology is going to be the most impactful and like the most useful? And at least for the short term, it kind of made sense that like finance was the most obvious application. I came to this realization after like working on startups that were trying to connect real world data on chain and just realizing how difficult of a problem that is. So I wanted to build like products that were sort of more circular, right? Like finance that relies on like on-chain assets. So that's why I kind of went towards the DeFi space, but I realized that I have like literally no finance understanding. So my undergrad was in electrical engineering, but I wanted to sort of build out that finance understanding. So I went and did a master's in financial engineering to sort of equip myself with some tools on this, which turned out to be a really good decision because this was kind of pre-DeFi summer. And then DeFi summer happened, and that was I was well positioned for that. I joined UMA in like early 2020. I was one of the early employees there, and the reason I decided to join them was spent a lot of time at hackathons and projects building out interesting like crypto primitives and sort of gadgets. We built like interest rate swaps. We built contracts with difference. We built like a bunch of different interesting things. And I kind of realized I was building a lot of the same tooling over and over and over again. So the decision was like, I'd rather build infrastructure that people can reuse rather than like, rewriting the same infrastructure a whole bunch of times. So yeah, that was basically my journey to UMA. At UMA, I've been involved with a lot of different things. I'm currently like the tech lead on the core UMA protocol team, where we maintain and like push forward this idea of the optimistic oracle, which we'll dig into a little bit. And I was also like somewhat involved or quite heavily involved in the design and implementation of the cross protocol, which is a optimistic cross-chain bridge that's powered by some of the infrastructure at UMA.
Nice. Nice. Yeah, I love when people become mission driven and decide to go deep down a rabbit hole and do crazy things like get extra degrees or try new things to get that level of experience. I think it makes you unique that you have the deeper financial understanding in addition to obviously the technical understanding as well. Working in DeFi, I mean, a lot of us have learned about finance and financial things just as a result of us being around, but I think it's good that you have that more holistic understanding. I'm sure that probably helps you. In terms of UMA, right? We'll talk a lot about UMA and the products you guys are working on there. But can you walk us through the optimistic oracle before we get into things at a deeper level? Because I think it's pretty crucial to understand what it is before you understand the rest of how UMA works.
Totally, yeah. So the optimistic oracle is our solution to what we call long-tailed data. So the basic thesis is that the way that DeFi is structured today is not the way that it's going to look in the future, right? Like right now, the vast majority of DeFi is around money markets, exchanges, and like some pretty basic derivatives products. And where these use oracles, it tends to be very simple information. So we're talking like the price of ETH BTC, the price of one asset in relation to another asset to power money markets is like primarily the main use case for oracles. And our sort of core thesis is that this is very much just the tip of the iceberg for oracles, and this sort of covers like maybe 10% of the future use cases of oracles. So if you sort of were to plot like the use or the complexity of data against the use of data, this very simple pricing information is on the left part of the graph, and all the other data, right? Like anything more complicated is sort of what we call this long tail. So at UMA, we're sort of targeting this long tail of data, which is arbitrarily complex and is only going to get more complex as DeFi becomes more composable. There are more projects built on top of it. There's more things going on within the space. So yeah, the core idea of the OO is to tackle this long tail information. And really the way that we achieve this is by using a fundamentally different oracle design versus more traditional oracles. So your normal standard sort of chain link oracle, we describe this as like a verify correctness in advance type of oracle, where you have like maybe a trusted actor or a group of actors who do some sort of verification and then push that information on chain. And there's normally very little or no recourse if that information is wrong, right? So it's like sort of trust or verify in advance. Our idea is to sort of flip this on the head and say that you enforce the correctness of the information after a dispute window. And this is where the optimistic component of the oracle comes in. So if you have any context of like how an optimistic rollup works, right, is what you would do is you would produce a whole bunch of transactions on the layer 2, and then you would submit like a bundle of these transactions on layer 1. And after some sort of fraud window, you can verify the correctness of those transactions if no one submits any fraud, right? So in like, or claims that there was any fraud. So in the happy path, the optimistic path, the system can evolve without any intervention, and only in like the unhappy path do we arbitrate. So an optimistic oracle works in the same way, but for pricing information or data, right? Any arbitrary data. So you would ask the oracle some arbitrary question. It could be like the price of an asset in the simplest case, but it could also be like, a complicated answer to like a Black-Scholes equation, or like something that requires like much more sophisticated information. Someone can then present a solution to this, and you sort of go through a liveness period where if no one disputes that solution, then it's taken as the word of truth. And if it's disputed, then there's an arbitration mechanism, which we can get into a little bit later. But yeah, so that's basically the high level idea, is around tackling this long tail for data in a sort of different structure, where we take advantage of economic incentives rather than trust in off-chain actors to actually bring on this more complicated data on chain.
Nice. Yeah. One of the things that excited me when I first started learning about oracles and the oracle problem in general was that long tail of data, right? I was kind of disappointed, like basically like a year into my time in crypto, thinking through all of these different opportunities to bring data on chain so we can build more advanced, like maybe just price feed related data applications. And it's cool. Like you guys have a UI, which I think is actually kind of unique for a system like this, where you can go in and you can see all of the different requests. And there's stuff like scores for baseball games and things for sports betting. It's cool to see all that. I want to get into like a specific like technical example, but do you have a favorite example of a type of long tail data you've seen used with the optimistic oracle?
I mean, so you mentioned like a polymarket request, right? So polymarket is a pretty big, if not the biggest, prediction market running on Polygon. And they use our optimistic oracle for their pricing information. And I think it's a great example, because you wouldn't be able to build an oracle solution that works at this kind of scale in many other patterns, right? Like certainly not in a push-based pattern like we use in a lot of other designs. So yeah, in that case, like all the poly market settlements for their prediction markets use this. And the really nice thing about this design pattern, which we can get into in the example, but the really nice thing about the pattern is that if the economic incentives are structured correctly, and you create the right bonding and incentive structure between the actors in this interactive game, right, between like requesters, proposers, and disputers. If you set those incentives up correctly, then you basically never have fraud on the system, right? And the reason is like if you commit fraud, you just always lose money, right? And that's kind of what we've seen since we've been on mainnet for like nearly 3 years now. Like we very, very seldom actually have people submit disputes. And I think that's like really seen in the poly market case, because the times in which we've had disputes, it's always been like when there's ambiguity, right? Or someone has like fat fingered something, but like people don't really like commit fraud, because the ramifications for doing that is just you literally just delete money. So yeah, I think, but yeah, the poly market's a great example, because it's by definition long tail information, like the resolution of an election, or maybe even something where you don't know when it's going to happen, right? Like maybe the sports game drags on longer, right? And you need like all these like edge cases where like the data just becomes like iteratively more complicated depending on how you structure it. But yeah, that's a good one. And we'll definitely talk about a cross later, which is also another example, right? Where like the information you're verifying in the oracle is around like, was some action that happened on one chain valid on another chain, right? Like that's what you're asking the oracle.
Yep, totally. So I do want to go to an example though. So let's just walk through the full life cycle, right? So there's, the listener can probably picture in general what's going on. Someone requests data. There's an actor that probably stakes money and provides that data. But can we walk through just like a full concrete example? So let's say that I'm the requester, right? That's the formal name. I request the price of ETH tomorrow. I think it's tomorrow, August 18th, right? Let's say you then are the proposer, right? You're proposing a price, and you lie.
Right.
You give an incorrect price. What happens next? How does that whole dispute process work, and what's the life cycle look like?
Right. So in the happy path, right? Like let's go with the happy path first. You would have asked this question: what is the price of ETH at a specific Unix timestamp? And you would have specified like a set of information that needs to be deterministic around getting that price, right? So we have like these things called UMIPs, which are like proposals around how prices should be resolved. So maybe we're going to take a median over a number of different exchanges that involves like a TWAP, as well as some other like, some very precise technique to come to the answer. So in the happy path, we would have taken that as valid after some parameterizable liveness period, maybe 2 hours, right? So in the unhappy path, I propose an answer and I'm bonded when I do this proposal, and the bonds are configurable. And some other actor would have seen, hey, that's wrong. Like either they didn't follow the rules of the UMA correctly, so the answer's wrong, or they've like genuinely provided like a completely wrong price with the intent of attacking whatever the requester is, right? To try and create invalid liquidations or settle a contract wrong or whatever. So in that case, what will happen is that you dispute the price, and we then escalate that to a system that we call the DVM, the data verification mechanism. And this is UMA's oracle or arbitrator of last resort. And what this thing is a Schelling point oracle, which is a concept that was introduced by Vitalik in Schelling Coin, which was a blog post, I think 5 or 6 years ago now, maybe longer. And the basic idea is that of a Schelling point is that you can construct an interactive game between players where the only correct behavior that they perform or that they do is to provide the right information. So the way that this works is your dispute of the price of ETH, right, would be enqueued as a price request within the DVM. And then voters, which are participants within the UMA ecosystem, would go through a voting cycle to actually vote on what they think the correct price should be. And we use a commit reveal scheme. This is where the Schelling point component comes in. So you need to commit to what you think the answer should be. And then in the following cycle, which is like daily, we run between commit and reveal, sort of tick-tock every day, you would reveal your answer. And because you can't see what the other voters are doing, the only thing that's rational to do is to vote with the correct price, right? And in the current implementation of the DVM, if you don't vote right, so you like either don't participate or you don't vote, then you basically miss out on receiving some inflation rewards that are issued. And that's the incentive for voting correctly. So if you vote correctly, then your balance or your share of the UMA supply grows and everyone else's shrinks. And we're currently like very soon launching a new version of the DVM, which is probably enough material for an entire other podcast. But basically in that design, there will be some other interesting mechanisms involving a staking system with slashing, as well as some other incentives. But the important point is that if you vote correctly, right, you participate correctly in the Schelling point, then you make money. And if you vote wrong, then you lose money. And the only thing that's economically rational to do, because you can't see everyone else's votes, right, is to vote correctly. If you could see the votes, there wasn't this commit reveal scheme, then it's obviously not a Schelling point. And the rational thing to do then is to just vote with what the whales do. But because you literally can't see it, you need to vote correctly. So we go through this commit reveal scheme. We come to the correct price of ETH on August 18th at a specific Unix timestamp. And then that price is then returned to the optimistic oracle. And we use that to arbitrate who was correct. Was the proposer correct or was the disputer correct? Right. And we then arbitrate who gets the bonds, right? Like either the person who proposed and was bonded gets it back, and then the disputer loses their bonds, or the other way, right? And you always have one actor was right. Either the proposer was right or the disputer was right. And what this means is you basically have this enforcement mechanism that in the case of fraud, you always go to the Schelling point oracle, right, which has like the entire UMA market cap behind it, basically ensuring the correctness of execution. Right? Because if the Schelling point is wrong, something goes wrong in the DVM, then for all intents and purposes, UMA will go to zero and the protocol fails, right? So that's all the incentives are aligned within the voters to always return the correct price. And then you use this to arbitrate what the voters do. I think a good mental model to think about this is, or the relationship between the DVM and the optimistic oracle is that if you were to cash a check and it doesn't bounce, you don't need to go to the Supreme Court, right? You can do that at the bank. But if your check bounces, then you go to the Supreme Court. So the DVM is sort of the Supreme Court in this game, and is always the arbitrator of last resort, or the oracle of last resort that resolves the fraud that may have been committed in the DVM. Oh, sorry, in the optimistic oracle. And it's designed in such a way that really we should only be touching the DVM like very infrequently if all the incentives are correct, right? Because if you make a mistake, you lose money, and therefore people shouldn't be performing this wrong, even if we have like a super high flow of requests.
Nice. Yeah, it's a really interesting model right? And I want to ask you how you came to this final design, or maybe I guess you're developing a new version of the DVM, so maybe it's still in progress. But I want to ask about that in a second. A couple of just quick follow-up questions on some of the details here, right? So a couple of things high level, and then I want to get into this ancillary data thing that I've seen in your repo. How are the liveness periods determined? Is that set at the beginning, or is that a common like just standard setting?
Yeah. So the liveness period is normally set at the time of request, and you would choose the liveness period depending on the security guarantees or maybe like risk assumptions of your product. So most of our systems use like a 2-hour liveness. We think that's sufficiently long that we can detect if things are offline. We can detect if things are done wrong, right? Because most of the time we can have like completely automated systems that verify these correctnesses. And it's also a long enough time that we're quite confident that we will be able to get a transaction on chain in that interval to submit a dispute, even if we don't know what the right answer is, right? Like you can always just be like dispute to sort of delay the timer in the event that there's fraud. So yeah, and you could make it shorter. And we do have some projects that have made it much longer as well. You know, if you're settling like a 3-year contract, it doesn't really matter if the liveness is like a day, right? If you want to be like completely confident in the correctness of that resolution.
Yep. Yeah, that's where the long tail comes in, right? There's definitely going to be certain types of data where that's right for. What about the bond? Is the bond set at the same time? So is the bond is that chosen by the requester, or is that again a protocol setting?
So all these settings can be chosen by the requester, right? They can choose what security properties they want for their request depending on their application. So this is also done by the requester. Normally you would want the bond to be some function of the amount of value at risk. So like in a cross V1, the bonds for doing a relay was like 5% of the relayed amount, right? So, you know, you don't want the bond to be some tiny amount if you're ensuring like a very large risk, right? So ideally these should be proportional, but these parameters are completely customizable, which is one of the things we've sort of realized needs to be have more aggressive defaulting, because sometimes it can be difficult to like know what the parameters to set are. So we make a lot of suggestions around based off of what your kind of product is and like how you're interacting with the protocol, how to set these magic numbers.
Gotcha. And then I mentioned a couple seconds ago, there's a field called ancillary data that I believe the requester can provide when they make a request. I saw this again. We mentioned the UI and things. There's a field where you can see what that is. It's all just, I think, just bytecode or some hash data. So I didn't go in and sleuth through it. But what is that? And is it useful for specific things? I'd love to understand what exactly that's doing.
Yeah. So ancillary data is kind of the secret sauce of why this oracle is interesting. So every request is uniquely identified by the identifier, timestamp, and ancillary data. So if you just have the identifier and timestamp, then you're somewhat limited in the kinds of requests you could make. Maybe you just ask the price of ETH at a specific timestamp. But ancillary data is what we basically define it as any additional augmenting information that you want to bring along with the price request. So in the case of poly markets or a cross, right, you would encode a complex data structure and put that in the ancillary data, and then use a more generalized price identifier. So for example, your price identifier could be yes, no query, right? That's literally the question you're asking. And then in the ancillary data, you could encode an arbitrarily complicated question, like the resolution of a prediction market, a cross-chain information, like anything, right? It's literally a bytes field. So you can basically view that as the secret sauce that turns this into like a Turing complete oracle, effectively. You can ask it any question and it will reply with an integer. So as long as your system can accept an integer as the reply to this question, which in almost all purposes is sufficient, right? It's like, is this correct? Yes, no. And with that sort of framing, you could encompass pretty much any kind of computation.
That's really cool. That's really cool. So can we go through a concrete example of that one too? That actually makes me really curious. So I was looking again through different requests for data, and I saw examples of sporting events, right? Mm-hmm. So I don't know, let's say there was one for like an MLB baseball game with like the Chicago Cubs and the Cincinnati Reds, right? I'm assuming I think there's still a price field that you have to include with your request, if I'm not mistaken. So I'm assuming there I put 0 for the price, or the price doesn't matter. And then what specifically, as a developer who's creating this request, what do I have to put in that data structure field? Like, or what's an example of something I would put? Is it like a
Yeah.
struct? Like, what does that look like?
So we have like a special encoding style that it's basically like bytes encoded JSON with extra steps. So we make like some small parsing on the JSON and then encode it into a bytes field. And in the case of like your sports game, the bytes field might just have something like, the JSON might just have something like Q equals, like for question, what was the correct outcome of this specific sports game at this specific time? And then the possible answers are 0 equals no, 1 equals yes, maybe a half equals invalid market, right? If the question was defined wrong, and maybe some special magic number equals that it was tried to settle too soon. Right. So what you would do is you would encode all the possible resolutions of your prediction market and sort of put this in a answerable question that anyone can answer. You encode that as a bytes field, and then you include that in the ancillary data when you submit the request. And then in this UI that you were describing, this would then parse that information and show it to proposers. And we have like a whole network of people who their whole like job, is to come here and submit price requests. And like, these are just community members, right? And the reason is that you get paid to play this game, to answer questions and verify other people's questions. There's incentives around this. So you would get paid to answer that question. And you could sort of rely on this proposal network that we've got to answer your question correctly. And if someone wants to do it wrong, then, someone will dispute it, and you kind of have those guarantees around the liveness around that. There obviously are requests that are much simpler and we can automate, and we do that if we can, right? If we can build a bot that can verify this, then we do. But a prediction market is a great example of something that you can't really automate easily, right? It wouldn't be like, you would need to use an API, but how do you encompass like any possible kind of question? And I don't know, it's not obvious like how you would automate that. So yeah, you kind of use this to encode the question that you're asking the proposers.
That's so cool. That's so cool. Yeah, I didn't realize. I mean, I guess I realized it was that generalizable, but to understand how it's working is very cool. That does definitely open my mind up to some possibilities. So I think this is a really good example of a crypto economic process that is very well designed and working quite well. There's lots of participation. There's lots of potential use cases. I mean, you guys have multiple products and products people have built on UMA around this. We have a ton of crypto economics and incentive related discussions at Superfluid because we have our own. I mean, I won't get into them today. We have our own systems we're designing and things like that require participation from a bunch of different actors that need to be incentivized in the right way. Do you mind like opening up the curtain on how this design process like went? Like how did you guys come up with this model? What were some of those early discussions like? I mean, I'd love to understand what the evolution has been like here.
Totally. So it was quite iterative. We started with the DVM in the very beginning, based off of the shelling coin idea, and built that into a primitive because we thought this thing is super useful in and of itself. But we sort of realized very quickly that this isn't like necessarily a scalable Oracle design, right? You can't have every UMA token holder voting on every kind of question. Like, that's not going to be scalable. At best, you want to have like maybe 1 or 2 votes a week at like absolute upper bound. There's coordination costs where voters need to come online, and it's expensive, and there's transaction costs and all of this. So we sort of looked around a little bit for some sort of scalability solution to this. And when we used to run the EMP contracts, which is the expiring multi-party contracts, which was one of the original synthetic assets we ran on UMA, we constructed this concept of a priceless financial contract. So the idea was to basically have an in-contract escalation game where you can run a synthetic, like a synthetic derivative of some kind, and you basically do not perform any kind of Oracle actions unless there is a liquidation. And only when there's a liquidation do you bring on chain information. And furthermore, we don't actually ask the Oracle for the price unless the liquidation is disputed. So you basically say like you can liquidate a position completely without actually asking the oracle anything. Because if you try and liquidate something wrong, then it will go through the same escalation path that we've been describing. And what that basically was like a specific implementation of this concept that's now generalized into the optimistic oracle. So we built some more financial products. We came sort of to the realization that there's this core primitive underneath, which is effectively like this escalation game. And we bundled that into its own little project or little product. And that gadget now is what powers all of our products and has enabled us to scale to handle, many requests in many different chains. And it's made UMA cross-chain native and generally unlocked like the potential of the system. And yeah, I think it's like a core mechanism for scalability, because if you don't have something like this sitting in front of the DVM, like you would be very limited in the way that you design these systems. The original use for the optimistic oracle was we were building out a perpetual version of the expiring multi-party contract. So we have like an entire product that would let you launch perpetual synthetics on Ethereum with like funding rates and a whole bunch of stuff, which we built, I think almost like 2 years ago now. And we didn't end up launching it for a number of reasons, but the really nice outcome of this is we had this gadget, which was the optimistic oracle, and we built it specifically for bringing funding rates on chain. So, it kind of was like this byproduct of another experiment, but just so happens that in and of itself is like a very powerful primitive that can power many different kinds of systems.
Yeah, that's pretty common actually. So in a lot of the conversations I've had with people in the space, a lot of this stuff, the rate of experimentation we all see for different protocols is so fast. And sometimes the things that end up really working are these adjacent things or these things we didn't think were the end real product, but became the real product, right? So it's cool. It's always cool to hear the behind the scenes. But
totally.
So we've discussed the optimistic oracle, right? This powers a lot of things. You mentioned poly markets, which is a prediction market built on UMA. There's also outcome, which uses, I believe, KPI options and long short pair tokens and things like that to incentivize people to do certain things. And then we also have a cross, right? And I want to talk about a cross because I think you've done a lot of work on a cross. And bridges are really important right now. They're very hot in terms of technologies right now. Can you just walk us through what a cross is overall? And I believe, it's an optimistic bridge. It's built on top of the oracle, so it has to be a kind of optimistic bridge. Would love to get the high level description, and then we can get into some of the specifics.
Sweet. Yeah, so a cross is a layer anything to layer anything bridge. At the moment, only supports Ethereum rollups and Ethereum sidechains, but in the future could support pretty much any chain where there is a canonical message bridge. And so at the moment, we're on Optimism, Arbitrum, Polygon, Boba, and obviously Ethereum. And it is a rift on a lot of the other bridge designs in how we treat liquidity, how we do compression with a lot of our data structures, and generally how we approach the bridging problem, which means that it basically works out to be one of the cheapest bridges in the space at the moment, especially in very large size. And the main benefit we get, or the main reason that this is the case, is that we treat the bridging problem more as a lending problem than as a swap problem. So a lot of other projects treat bridging as like a swap where you have AMMs on each side of the bridge. We treat it more as a loan between the relayer and the protocol and the person actually doing the bridge. And that means that we can have like different kinds of fee models and manage our capital in different ways, and basically results in like a very cheap and very fast product for moving between these different chains.
Yeah, so you have one thing you mentioned around the way you're treating the problem. Is one thing you have, I think that's helping solve this, is this really interesting hub and spoke model for liquidity. Can you walk through what that is and how you guys even came up with that?
Yeah, totally. So the idea is rather than fragmenting your liquidity over all the chains that the bridge operates on, you let the protocol decide where to allocate the funds and rebalance the funds across different chains dynamically as supply and demand evolves. So what this means is you don't fragment your liquidity across these chains, right? You can be much more concentrated in where you put your liquidity. So specifically what we try and do is keep as much of the funds on layer one as possible. And then we can reallocate this to other places where needed, because going from layer one to Optimism or Arbitrum or any of these chains, it's much faster than bringing the funds back, right? So you kind of keep it in the location where things are quick, and then you deploy it dynamically when you need to. And yeah, so I mentioned that we sort of view this as a lending problem. And the way you can think about this is like, and where this fits in with the hub and spoke, is if a depositor, let's say, is trying to move from Arbitrum to Optimism, effectively what we do is a relayer will front you the capital on the destination chain where you're trying to go to. And then the protocol pays back the relayer within a liveness period. And this is the liveness period we discussed before with the optimistic oracle. And then the protocol takes on like the rebalance interval. So you basically have like two nested loans. The relayer is loaning the recipient money, and that's how they get an immediate fill, right? So the relayer has money on the destination chain, you make your deposit, the relayer pays you immediately. And then once the relayer is repaid after 2 hours, right, they get paid back from the protocol, which comes from the LPs. And that's sort of where the repayment component comes from. And then the LPs then effectively take on like the rebalance time part of the loan, where we might be moving those funds like back to layer one, or maybe we're moving them between different chains or whatever. And all of this is obviously handled in like a permissionless way by leveraging the optimistic oracle to verify that the execution of the protocol is done correctly. So yeah, that's basically how the hub and spoke fits in with the loaning. Is like you can have one central component that sits on layer one, which is the hub, and we call this the hub pool. And then each of the layer twos have a spoke pool deployed on them. And the hub pool can basically dictate to the spoke pools when they should move funds between the different chains, how the rebalancing should happen, when to repay relayers, like all this kind of stuff. And that's all optimistically enforced using the optimistic oracle. You asked also like, how did we get here? So V1 of across was just a fast exit bridge. So in V1, we had these deposit boxes on all the different layer twos, and then a hub on layer one. And basically LPs would deposit on layer one, and it would basically let you exit from a roll up to layer one in like 2 minutes, right? As opposed to having to wait the 7-day liveness. And then it's the same concept, just simpler, right? What you're doing is you're borrowing money from the LPs, and they're paying you immediately. And then the LPs then wait for the full duration of the transfer from layer two to layer one, right? And then obviously there's a lot of stuff we can do around like grouping a whole bunch of transfers together and bundling and all of this, which I'm sure we'll get into in a bit. But in V1, you could bundle together like a whole bunch of different transfers from layer two to layer one. And you can do these kinds of things to make this process like a lot cheaper. You can amortize the cost of these expensive operations by doing them in sets together.
Got it. Yeah, that's very cool. Can I also pass arbitrary call data along with these messages I'm sending cross-chain? We talked about ancillary data before, right? Where I can create these custom data structures that I encode, that I can get information back in terms of just the oracle itself. But can you also like make cross-chain smart contract calls and do those kinds of things, or is it just strictly around liquidity?
Yeah, for now it's just tokens. Reason being that token transfers and how we think about moving funds around is easy to reason about a lot of the risks associated with this. Like you can quantify the cost or the risk of the transfer by the amount of assets that are moving. But how do you necessarily do that with like a cross-chain function call? Like I want you to call this admin contract on layer one from Optimism, insure it with X amount of dollars. Like, I don't know. It's not clear how you do the pricing effectively, and the insurance thereof. And there's also other complexities around like how you would design aliasing. So you would ideally need to have like some system where you could verify the originator of a function call on another chain. So yeah, these are definitely things we're thinking about. But for now, like the problem space is bridging tokens, and if there's a V3, which maybe it will include something like this, but yeah, not something that we actively support at the moment.
Mm-hmm. And then you mentioned bundling a bit ago. I think this is a really interesting pattern you guys use. I'd love for you to understand. I'd love for you to explain what bundling is for our listeners, and I want to go deep into these because I think these are interesting.
Yeah. Okay, so this is really where the product differs from a lot of the other products that do similar sort of things. Bundling as a word is like pretty overloaded, and we use it in a whole bunch of different ways. But I'll try to unbundle the bundles a little bit. So we have the first kind of bundles are different kinds of data structures that we construct to do different things. And there are three main kinds of bundles that we construct. So the first one is a pull rebalance route, which basically is used to push or pull funds to and from the spoke pools from the hub pool. And this could contain potentially many tokens in one bundle, going to many different chains, many different transactions all grouped together. We also have a relayer repayment or relayer refund bundle, which is used to refund relayers against a set of valid deposits. And the last one is slow relay bundles, which we use to pay recipients directly from the hub pool in the event that relayers run out of money. So the basic structure and the way that these bundles work is you'll have depositors and relayers basically interacting with each other on all the different chains. So depositors are moving funds from different chains from chain A to chain B and chain B to chain C and back and forth and all of this. And the relayers are there sitting and watching these deposits and filling them, right? So you're calling like fill relay on the contracts and you're filling these relays. There's a third actor who sits off chain and sort of watches all of these different actions happening across the entire ecosystem of contracts. And we call this person a data worker. They then group together all the different transactions that they've seen happening across these chains and construct bundles, which they then submit to the hub pool containing these three routes that I mentioned. So the pull rebalance route, the relay refund route, and the slow relay route. So they watch all these actions happening on all the chains, they build the routes and they submit them. And they call like a submit relay route bundle or submit route bundle method, which contains the root of these bundles. And to dig a little bit deeper into what the structure of these bundles look like, if we consider like the pull rebalance route, right? What this is a root of a Merkle tree where each of the leaves within the Merkle tree is a different kind of operation. And it might be like, it might instruct the hub pool to tell a spoke pool to send funds somewhere or to repay a relayer or to rebalance its assets between chains. So what you're doing basically as a data worker is you're watching the system, you're implementing the rules of the UMIP, which I mentioned when we spoke briefly about the optimistic oracle earlier. And you're saying, okay, based off of the rules of the UMIP, Arbitrum has too much funds in it, and we need to pull those funds back to layer one. So I'm going to construct an instruction to do that. This is the pull rebalance route. And then you put it in and amongst all the other actions within this Merkle tree. You construct the tree and out comes this root of the Merkle tree. And that's this pull rebalance route that you submit to the smart contracts. And then the reason that this is so cool is if you're another data worker or you're someone who's sitting off on the side, all you need to do is look at three numbers or 3 bytes 32s to verify the correct evolution of the system over all actions, right? Because you could independently be like, okay, I can see all these relays, all these repayments, all these rebalances that need to happen based off of the definition of the rule set. I construct my own Merkle tree independently, right, for these three routes. And then I can compare, was the one that was submitted, does that match my expectation? And if it doesn't, then you dispute it. And we go through the escalation process we spoke about earlier. But if it does, then you know that the data worker has submitted the correct action. And then the system is like good to go to do the next step, right? And the next step might be rebalancing, repaying relays, or filling slow relays, right? Those are like the three main actions that the system can do. So that's like kind of a lot of stuff going on, but the really nice component about all of this is that we have like, this very complicated system that boils down to like 3 hashes that correctly verifies the correct evolution of the system. And those hashes are either right or wrong, right? So the identifier that you ask in the optimistic oracle is literally like a cross V2 bundle. Like you're checking if these 3 things like correctly implement the UMIP. And if it does, then the system can evolve. And the next step, what happens is once this bundle gets through liveness, the smart contract then stores the roots of the Merkle tree within its state. And then another data worker or the same data worker can come along and actually execute the leaves. So what you would do is you would take the leaf, let's say that's to like rebalance one of the pools. You would submit that as a JSON or like as a struct to the contract along with the Merkle proof, right? And then the contract can verify that that leaf was part of the original tree that was presented because it has the root that got through liveness. So you're doing an inclusion proof to prove that the leaf that you presenting it, the contract with, is valid. And then if it's proven to be valid, then the contract can execute this action, which might push funds, pull funds, repay relayers, do whatever the action might be, right? And that's kind of the secret sauce with this is in being able to compile complex operations into like very succinct proofs. And if those get through liveness, being able to execute those in like a multi-chain space. And that's kind of what makes it interesting. So yeah, that's the primary layer of bundling. We also bundle like transactions together, but that's like kind of less unique in that we use like multi-call to do like multiple fills at the same time. So we can fill like, 500 fills at the same time in one transaction. And then you get some benefits with like fixed cost of submitting transactions and state warming and all of this. But yeah, that's less of like a bundle in like the cross sense and more just like a bundle of transactions, which is a bit more standard.
Super cool. And then what are you guys using for some of the cryptography in all of this? So did you guys write like your own library to manage some of this in contracts? You're using I know OpenZeppelin has I think like a Merkle proof library that's pretty helpful, but is there anything you've used that's been helpful?
No. So like rule number 000 is never roll your own crypto, right? So we're definitely definitely not doing any of our own cryptography. Merkle trees are very common data structures. So we're just using like a standard library for that and the OZ library for verifying the correctness of these bundles. So yeah, no, definitely nothing too fancy there. Like the complexity more comes in like defining the structure of the leaves and like how you take this leaf that's submitted to the hub pool and like translate that into an execution that needs to happen. And like all the permissioning across chain and like doing all of this in a way where it's more permissionless, right? Like that. So that's more of the complexity than the cryptography. Try to keep the cryptography simple.
Makes sense. And what does the structure of one of those leaves look like, right? I mean, these are, I think, individual transactions and operations. Can you walk us through like specifically what one looks like?
Sure. So the simplest one to understand is probably the relayer refund. So the relayer refund, like let's say you're a relayer and you've filled a whole bunch of relays on a whole bunch of different chains, right? So you filled relays on Arbitrum, on Optimism, on Mainnet, whatever. And when you're filling these relays, one of the features of a cross is that the relayer can actually choose where they want to be repaid, which is kind of nice. So they can get, they filled something from Arbitrum to Optimism, but they want to be repaid on Mainnet, right? For doing that action. So if let's say this relayer chose to do all these relays and get repaid on Mainnet, then the relayer refund leaf would look something like pay this address, this amount on this chain of this token, right? Like, and that's again where like the sort of meta bundling comes in, because you're repaying a relayer for potentially many actions all within one transaction, right? And then that's bundled then again with all the other relayer repayments that all happen within one transaction. So, you may have filled an undefined many relays and you get repaid in one aggregate step. And that's really where the cost savings come in and why it's so cheap.
That's really cool. Yeah, there's a ton of efficiencies in there. Yeah, and when I was kind of breaking into what this was and how it was working, I was kind of swimming through the docs and things. You had a video I think I watched as well on it. Yeah, it's definitely very cool, and it's a pattern I think is very unique to what you guys have done. And on that note, right? So what I think I'll try to ask in a lot of these interviews is, what are some of your favorite patterns or gas optimizations or anything you've really done inside of the UMA contracts that you're personally proud of that people from the outside might not see? Like, is there anything that is a favorite of yours?
Yeah. So gas optimization is obviously, there's a lot of nuance to that. So we do all of the like normal gas golfing stuff that you would probably do before launching a project on mainnet. So, minimizing state reads and writes and using the correct types if you can compress them, and doing state packing and all sort of like the stuff you would find on a Medium post. We obviously do all of that. I think where things get more interesting is trying to design your system from a cost first perspective, right? And this is something that's taken us a lot of iterations to get better at doing. And this like bundling discussion right now is something, we thought about specifically to try and not just make things like a little bit cheaper, but to actually make them like orders of magnitude cheaper, like trying to construct your design in a way where you layer savings on top of savings, and you get like this multiplicative effect rather than just like, I managed to make a for loop cheaper by using like an unsafe increment or something like that. So I think there's like different ways of viewing gas, and really like our focus where this is important, right? Which isn't always the case, but where it's important is to design first thinking about that. And then the other thing I would say is, like I mentioned earlier, using like multi-call for off-chain actions. I think this is something that's like pretty underutilized a lot of the time. So our bots and like relays in the community and like people running relay bots, right? Like often you'll be filling a lot of relays at the same time. So a pattern, for example, here where you can be cheaper is maybe it's okay to slow down your bot a little bit, right? You don't have to fill it as soon as you see it. Maybe wait like a minute, right? And that way you can collect a whole bunch of fills that have all come in at the same time, and then fill those all in one transaction, right? And that becomes a lot cheaper because you benefit from not having to pay the fixed cost per each transaction. And like the state warming refunds that you get in the EVM is like non-trivial, right? Like if you access the same piece of state multiple times in the same transaction, you get refunded, and like subsequent requests become cheaper, right? So slowing down your system, and this is obviously only applicable really with like off-chain actions calling on-chain stuff, but that's quite a lot of systems have those kinds of flows. So yeah, slowing things down a little bit to try and group stuff together and just take advantage of multi-call, I think is like a pretty non-trivial saving. Something like, in our case, I think it was like 30 to 40% saving versus like filling every relay as soon as we saw them. And like the impact on the user is not like really that big. It's like, either it took 5 seconds to fill or like 50 seconds to fill. Like it's probably okay in most cases.
Yeah, 30 to 40%, that's quite a lot. Yeah, I think having that mindset that is cost first is something that is a bit unique to our space, and that there's literally money and cost embedded into everything, every operation, right? What at UMA is your process for like design, development, implementation, maintenance? Do you guys have any methodologies that you use for your development process? This is something I asked someone from our team to come up with a couple of questions for you and another guest I have today. And this is one of the main questions that came up. He's a protocol dev on our team. Would love to understand if there is any behind the scenes on how your process looks.
Yeah. So it depends very much on what we're building and how complicated that is and how clear the path to implementation is with that. But I would say in broad strokes, we try to always come up with a sufficiently well specified design doc before starting to write any code. I chose those words carefully because over engineering in the design phase is normally not worth it. Mainly because like you don't really know what you don't know until you start writing code a lot of the time. Like sometimes you actually need to like, git init before you can figure out, oh, there's a problem with this data structure or this doesn't work. So yeah, what we normally try and do is come up with like a sufficiently well-defined doc, which explains maybe the interfaces, maybe what they do, and specifically focusing in on like the mechanism within the contract rather than like implementation specific stuff. So if it's a system like a cross, it's around discussing like, there's like many different ways to build a system similar to a cross. And we had like many iterations on the design, and it's really like discussing the variance in the mechanism itself at like a high level and not getting too bogged down by the details. So trying to come up with like a conceptual model of the product first. If it's a simpler thing that you're building, then maybe that can be like a very short, like couple paragraphs, and then you just start writing code as soon as possible. But if it's complicated, then I think definitely spending time on the design phases is important. Then other things we found useful in this process is when you're collaborating with other engineers on smart contracts in particular, I think a really good pattern is to start off by first defining the interfaces for your functions in your first pull request, right? Or like the first couple PRs. So you would write like, this is what I think the structure of the smart contract should be. And within each of them, you write like a body of comments explaining like, this is what the internal logic should be. This is how it's going to interact with the other contracts. And you can then get feedback from other engineers on your team on like how you've laid things out, the way you're thinking about the problem, and like importantly, naming, right? Like naming things is really hard, and like engineers are really bad at it. So trying to get some feedback on that as soon as possible before you spend like days writing like some complicated logic. So doing that, I think, is really important. And even if it's just two of you working together, right? Like split up the problem and chunk up who's doing which component, and then get the feedback on the interface. Like it literally is like the function definition and a block of comments. It's like, you can talk for days about that until you've actually honed in on like exactly what they need to do. So once you get to that phase, then one thing we try really hard to do is to keep the implementation as incremental as possible and as small in pull request size as possible. So like never more than like 100 to 150 line diff in Solidity, plus like maybe the same amount in tests per time. Always keep it small, because if it's too long, then reviewing it is actually difficult. And also if you find like, hey, doesn't make sense, or like, you made it like a fundamental mistake, you now have spent like 2 days writing it and you got to delete all that code. So keep it small. And another thing we do, which is maybe unconventional, but we found to be very useful, is we don't write unit tests until we've gotten an initial round of reviews. And reason is like, you can look at the Solidity and be like, hey, this is wrong. Great that the test passed, but that doesn't really mean anything if it like either doesn't make sense or like there's a better way of doing it. So yeah, the incremental process, like once you start writing code, like function definitions and comments, then initial implementation of the function definitions in an incremental way, and then unit tests sort of as you go with each of these chunks of work. I'd say that's like really for us has been really useful. The other thing is, which is like once you've actually gone through the process and you've got a finished product, writing life cycle tests and like end-to-end tests more than just unit tests, I think is very important. So you've got this complicated system of many components that interact with each other. Write like a mock life cycle that goes through every single step along the way, and you sort of embody a user in the system and sort of tell a story or a narrative that you paint with the test. User one does this and deposits this, and like it seems kind of obvious, but like a lot of the time people will just write specific unit tests that just test single functions, but like pulling it all together, often you can find problems or just identify like further optimizations or changes that you might want to make in places before you send things away to get audited, and at which point it's like much more difficult to do that iteration cycle.
Totally. Yeah, we second you on naming. We struggle with that sometimes too. And we've also gotten a lot of benefit out of really high quality detailed mocks. So I think that's really good advice. We're coming up on time, so I'll only ask another question or two. But before I get to the end, do you guys do anything specific or have any specific thoughts on security and maintenance?
Yeah. So we care a lot about this. We've been on mainnet for like 3 and a bit years and like haven't had any major security vulnerabilities, like touch wood, obviously. But like, I think a lot of that is a symptom of or a function of us like taking this very seriously. So I think the main thing is being very serious about your audit process and like trying to set the auditors up to succeed, right? So what that means is like, don't give auditors code that has, typos in it or is like incomplete or whatever. Like try give them code where they can focus on the hard problems rather than like needing to like nitpick a whole bunch of stuff. And like I say that, and we just got an audit back that had like a whole bunch of nitpicks, but still ideally try and give the auditors the best kind of code as possible. And obviously don't change code after the audit where possible without getting them to check, because that's just like, we've had a lot of vulnerabilities in the space where things like that have happened. So I think that's really important. And then also, I think there's a lot to be said for like on-chain monitoring around the health of systems. Like you can construct a lot of primitives or a lot of like heuristics that you can impose on your contract. And like, if these things don't hold true, then, like sort of like invariant checks, then maybe there's something going wrong or someone's doing something weird, and you might be able to intervene before it becomes too late. So I think monitoring, on-chain monitoring with tools like Tenderly and Hell, or maybe like custom bots, is like a big thing that a lot of projects don't focus enough on.
Makes sense. Makes sense. No, it's good to hear how a protocol like yours that's done a very good job with it approaches that process. So hopefully people listen to that advice for sure. Before we wrap up, I want to get to understand how you think about the space more broadly. And I'll give you two. I guess I said one or two more questions. I'll ask you two quick questions now. On the first one, let's say you had 6 months. You've done a lot of hackathon work. Like if anybody goes and finds you on GitHub, they'll see a ton of output. If you couldn't work on UMA for the next 6 months, right? Let's say someone says, holds a gun to your head and says, you got to work on something different. What would you spend time on?
Yeah. I think like I'm pretty interested and have like spent a fair bit of time messing around with MEV related stuff. And I think there's a lot of untapped across chain MEV, which is pretty untapped. And there's like potentially orders of magnitude more MEV to extract in that space. So that's just me personally. But if I was to say like other primitives that I think are interesting, I think that NFT derivatives in particular are still in their big infancy. So, we've got like pretty deep and liquid, or maybe not liquid, but there's definitely lots of NFT marketplaces and like new designs that are coming up. But derivatives built on top of these are like really not like a thing yet. So like perpetuals on NFT prices, floor perps, this kind of thing, I think are going to be huge the next time there's a big NFT cycle. Right? Like if people think things are overpriced or underpriced, like creating a venue where you can speculate on this is just going to be huge. I think also like bribery in like bribe systems like Convex, Vodium, these kinds of like things within the Curve ecosystem are like really, really cool. But there's a lot to be improved still on that. And like generalized bribery, sort of like what Covenant Protocol is building, I think is very, very interesting, and like a lot to still be unlocked with that. And I guess last thing would be, I really hate how dependent we are on Etherscan. So I wish there was like a decentralized Etherscan that someone builds, that's like not, that's somewhat censorship resistant, or is just like an alternative, right? Like if Etherscan goes down, Ethereum might be off for all intents and purposes for most users, right? So like that's bad. So I think fixing that would be pretty cool.
Yeah, we have a guy on our team at Superfluid who's obsessed with this problem of a decentralized contract verification thing, right? So I'll pass along that to say he's got some support if he figures it out. Okay, final question. Let's say we zoom out, we fast forward to 2032. It's 10 years in the future. What do you hope our industry looks like? Like, what do you hope things have transpired to become?
Oh wow, that's a wild question. So I can first tell you what I hope it doesn't become. So I guess the main thing is like there's been a lot of scary stuff going on at the moment with potential regulatory capture of a lot of things. So I hope that doesn't transpire in an unthoughtful way, right? Like there's a path where regulation is like, I think regulation is important when done in the right way, right? Like you don't want to stifle creativity and industries and things like this, or like over-regulate spaces. So what I hope doesn't happen is that things get regulated into oblivion and we just become a permission chain. So that would be the first component, is like this is still in some ways it's like well regulated but still accessible, and not like just a completely policed system, because then what have we built? What is the point of this whole thing? What I do hope happens is that a lot of this stuff, like people don't even need to know that they're using it. Like the more behind the scenes a lot of this technology becomes, I think the better. Like this should, for all intents and purposes at that point, be mostly like, HTTP in your experience with the internet, right? Like it's a piece of a broader stack, right? I don't think like DeFi or a lot of this crypto stuff just for crypto stuff's sake really makes sense in a 10-year arc, where if we've reached like true mass adoption and all of this, it should just be like the default assumption that this is the technology that's powering it, as opposed to it being like front and center. So I would say like the space has grown. 10 years from now, I'd love to see that the space has grown to a point where we've reached some semblance of mass adoption, whatever that means. Maybe it's powering like applications that people use on a day to day to facilitate who knows what. It's like asking what would Uber look like in 1990, but it's powering a lot of things that people can provide value and can derive value from in a way that they don't even know that they're using the tech. Like if we reach that point, then I would say we've succeeded. And if we obviously maintain the ideologies of the space, which I think are really, really important, like permissionless, decentralized, and censorship resistance, I think are like they're sort of fun buzzwords, but they're also like become more and more important when there's like threats of state capture and things like this, which should be taken pretty seriously. So yeah, I would say that's basically my goal, or what would my definition of success would be.
Amen to that. Well, Chris, this has been a lot of fun. Thank you so much for joining us today.
Yeah, thanks for hosting this. It was great.